Hello everyone, I'm Gareth. Today I will explain how wind stress creates large ocean gyres, and how these gyres lead to western intensification and finally the Gulf Stream. I will also explain all the important physical relationships in simple languages, so they are easy to understand. First, I will start with wind stress. When wind blows across the ocean surface, it pushes the water, but because the Earth is rotating, water does not move in the same direction as the wind. In the northern hemisphere, the net movement of the upper ocean is about 90 degrees to the right of the wind. This is called Ekman transport. This simple relationship acts like a formula. Net transport equals to 90 degrees to the right of the wind. This happens because each thin layer of water is pushed by the layer above it, but the Coriolis force keeps turning the water to the right. After adding up all layers, the final movement is sideways. This sideways transport creates areas where water comes together or spreads apart, which is the starting point of the gyres. Figure 2 shows the structure of the subtropical and subpolar gyres in the North Atlantic. The arrows on the map show the large-scale interior flow produced by wind forcing. The only formula type symbol on this page is beta, the beta effect. Beta describes how the Coriolis effect becomes stronger as we move north. Because the ocean must conserve vorticity while the Coriolis effect changes with latitude, the interior flow adjusts in a predictable way. This gives us the severe jump flow, which is the broad and slow equatorial transport inside the subtropical gyre shown in Figure 2. Figures 4a and 4b show how western intensification develops. Figure 4a illustrates that the interior flow is wide and weak, but the return flow becomes narrow and fast on the western side of the basin. This happens because the increase of the Coriolis effect with latitude forces the adjustment to occur in a thin western boundary region. Figure 4b shows the real ocean example along the US East Coast. The bright narrow band represents the strong western boundary current. This image helps us see that the theoretical pattern from Figure 4a actually appears very clearly in satellite observations. Figure 5 shows the satellite image of the Gulf Stream. The first relationship here is pressure gradient balanced by the Coriolis force, which is geostrophic balance. The current flows along the lines of pressure because these two forces match each other. The second relationship is thermal wind balance. It's the density gradient creating vertical shear. One density changes across the current. The speed varies with steps. This explains why the Gulf Stream is strongest at the surface and weaker below. Figure 5 highlights the structure, a narrow, fast surface jet that fits both geostrophic balance and the thermal wind pattern. To summarize, the right-hand side of this slide shows the full sequence that creates the Gulf Stream. It starts with wind stress, which drives Ekman transport and Ekman pumping. When the wind stress changes across the basin, it produces wind stress curve. And this curve controls the interior circulation through the severe jump flow. As the water moves across different latitudes, the beta effect becomes important because the Coriolis force gets stronger towards the north. This forces the return flow to concentrate along the western side of the basin, creating western boundary intensification. When all these processes work together, they produce the Gulf Stream, a narrow, fast, and powerful western boundary current. This change shows that the Gulf Stream is the final result of wind forcing, Ekman dynamics, and the changing influence of Earth's rotating. And this is my references. So thank you very much.